Hi, what is a moment? Now, in the previous chapter, we have learned that forces can cause objects to accelerate. In this chapter, we will learn that forces can also cause objects to rotate, and the turning effect that this force has when it's applied on an object, that is called a moment. Okay, so here's how you can think about it. Clockwise moments will cause clockwise rotation. Anti-clockwise moments will try to cause anti-clockwise rotations. So, in a given scenario, when you have forces acting on an object causing both clockwise and anti-clockwise moments, what you have to do is you have to sum up the total clockwise moments and the total anti-clockwise moments, and then you compare the amounts. So whichever side wins, the object will rotate in that side. Okay, so if you have more clockwise moments, then your object will rotate clockwise. If you have more anti-clockwise moments, then your object will rotate anti-clockwise. Then finally, if you have equal amounts of moments, so if your clockwise moments equals to your anti-clockwise moments, then your object does not rotate at all, right? Your object will be in equilibrium. And that is actually summarized in this principle of moments that I know everybody tries to memorize. Remember, for an object in equilibrium, the clockwise moments equals to anti-clockwise moments about any given pivot, right? So that's basically summarized in this diagram here. Okay, so the chief things that you need to consider when calculating moments is, first of all, where is the pivot? Right, this is in easier questions, this is usually given, but in harder questions, you have to decide for yourself where do you want to choose as a pivot. We'll have some examples on this later. Okay, so once you found the pivot, the next thing you have to do is to draw the line of action of a force. Now, line of action of force is this thing that I have here in this dotted line. So when a force is exerted, it's always exerted in a particular direction, right? That's because a force is a vector quantity. Remember, it has a direction to it. So what we do is we extend this imaginary line here, right? That the force is acting along, right? And this is known as the line of action. And what you want to look out for is this distance d here, which is the shortest distance between the pivot and the line of action of this force. Right? Now, most of the time in school, you will learn this as the so-called perpendicular distance. Okay, but perpendicular distance, I think, is a little bit confusing because sometimes people get confused where is the right angle supposed to appear. So it is much safer if you choose just the shortest distance. Okay, and the shortest distance will also happen to be perpendicular. So for this example, look at this. Like, what is this distance shorter? Is this distance shorter? Which is the shortest distance? The shortest distance will be this one, right? The one that is perpendicular. Okay, so if you're ever confused, just look for the shortest distance. Now, why we want this distance is because we want to calculate the moment by taking the amount of force here, multiplying it by this distance here. And this is the amount of moments that we have. Okay, so for this force, we can see that it's going to create anti-clockwise moments with respect to the pivot. All right, so let's look at some examples. Okay, so let's try to apply what we have learned in this example. If you want to, you can pause the video here and try this out for yourself first. If not, then let me go through this question with you. So what we have here is we have an angled beam attached to a spring. The pivot is given here. So this is one of those easier questions where the pivot is shown. And we can see here that there are several forces acting. First of all, we have a 800 Newton force here acting down on this end, and then the spring is pulling down with 160 Newtons, and then we have one unknown force which we're supposed to find here. So first of all, you recall what we have to do, right? We have to first find our pivot. Second, we have to draw the line of action of force. Now this is for choosing the correct distance, right? So this 800 Newton force, the line of action is here. And so you can see that the shortest distance from the pivot to the line of action, that will be the 2 cm. Okay, and this force acting downwards on the left, if it were to act downwards, is going to cause a anti-clockwise rotation, right? Then next we have this spring force. Line of action of the spring force is over here, and you can see here the question is actually trying to trick us a little bit. It's given us this 5 cm here and this 4 cm here, and so what it's trying to test you is to see whether you know which distance to use. Okay, so if you follow my method, what's the correct distance to use? You're supposed to find the shortest distance between the pivot and this line of action. So you can see obviously the shortest distance would be this one here, right? 4 cm. Okay, so that would be 600, sorry, not 600, 160 multiplied by 4 cm later. And then finally this last one, we have this unknown force which acts along this line. And then the shortest distance between the pivot to this line of action again would be this horizontal distance here, 8 cm. Okay, not the diagonal distance here, 10 cm. Okay, so always remember shortest distance. All right, now they are saying that this force F, right, is the amount of force required to keep this in equilibrium. In equilibrium means, in this case, not rotating. Not rotating. Okay, so not rotating means your clockwise and anti-clockwise moments must be equal. Okay, so the 160 newtons, this is going to cause clockwise, this force F is going to cause clockwise as well. Okay, so let's write down our principle of moments first. The clockwise moments must be equal to the anti-clockwise moments. Okay, so clockwise moments would come out from F multiplied by, what's the distance? 8 cm, right? Plus 160 newtons times 4 cm. Okay. And then the anti-clockwise moments would be 800 multiplied by 2 cm, 800 newtons multiplied by 2 cm. Now, notice that I'm not using the SI units. Most of the time, you're supposed to convert this to meters first. But in this case, because every single distance I'm using is in centimeters, so if I have to convert, I will basically have to multiply both sides of the equation by the same amount. So it will cancel out anyway. Okay, so it doesn't make a difference in this particular case. Normally, you would need to use everything in meters. Now, solving this equation, right? If you solve this equation, you should get the answer F equals to 120 newtons. Okay, I hope you managed to get that. Let's look at the next example. Okay, so this example is slightly more difficult than the first one because of two reasons. Number one, you don't see the pivot given in the question. Okay, and number two, instead of all the forces acting in the same direction, now we have some forces acting in the vertical direction and some other forces acting in the horizontal direction. That will affect how you choose the correct distance to multiply each force by. So pause the video here, try the question yourself first. Okay, so assuming you finish trying the question, you can let's go through the question now. So first of all, like I mentioned, where should we choose as our pivot? We should choose this point. Okay, why? Well, if you try to imagine this barrel rolling up the step, it's going to be pivoted about this point. Like this is the center of the rotation. Okay. Second of all, you can consider that there will be some amount of force that the step acts. The step is going to exert some force on the barrel here, right? And this will be a very tricky unknown to deal with. And so we can avoid dealing with this unknown by choosing this point as the pivot, because then the distance between the line of action of this force and the pivot would be 0. So then we wouldn't have to deal with that force in the equation. Okay, so now this point is the pivot. The next step would be to look for the line of action of each force. So for the weight, quite simple, line of action is over here. Okay, and for this horizontal force, the line of action is this way. Okay, so what that means is that we can find the appropriate distances now. So for the weight, what distance should we use? We should use the shortest distance between the pivot and this line of action, which happens to be this distance over here, this 0.4 meters. And for this horizontal force, the shortest distance from the pivot to this line of action would be this distance here. Now, this is not given, but you can quite easily check it out by looking at this 0.5 and 0.2, which means that this distance should be 0.3. Okay. Now, we can identify also that our weight is going to cause, well, it's trying to make the object rotate this way, whereas this force is trying to make the object rotate this way. Okay, so given that, now, if we want to find the smallest value that can cause the barrel to roll up Roll up would be rolling this way, right? So this is the anti-clockwise direction. So what this means is that our anti-clockwise moments has to be slightly greater than our clockwise moments. Okay, so now that we've written this out, we can just put in the calculations. So that anti-clockwise moments would come from this force F, which we can calculate by taking F multiplied by 0.3. And this has to be greater than the clockwise moments due to the weight. The weight would be 300 kgs multiplied by 10. Remember, you're supposed to know G equals to 10 Newton per kilogram, right? This is assumed knowledge. So this is the weight, and then you have to multiply by the appropriate distance, which is 0.4. So if you go ahead and solve this, you will get F has to be greater than 4,000 newtons. Okay, so 4,000 is the minimum amount. Okay, let's go to the next example. Okay, next example. Now, earlier on, remember we looked at the thought process where clockwise moments versus anti-clockwise moments. Moments are the thing that cause that object to rotate. So we can use this logic to help us to do an explanation question as well. So this question, we have this one of these balancing toys. The center of gravity is given here, and the toy is pivoted at the beak. Okay, and when it's displaced in a direction like this, they ask us to explain briefly why the toy returns to its rest position. So when they say explain, remember, explain always means what is the cause. Okay, so if you have studied this in terms of cause and effect, then you will have a very easy time with this, because we learned about cause and effect here, right? Where the cause is the moments and effect is rotation. So just from here, they are asking what is the cause. So can you see, what we have to say is like something creates moments and then the moments causes rotation, right? So what creates moments? If you think about it, the center of gravity is over here, directly like where the beak is pointing. So once you rotate this object, center of gravity should be somewhere over here now. So that means that the weight is acting down, gravity is pulling down at this point, whereas the pivot is here. Can you see that this is going to cause clockwise moments? Okay. So just by understanding this in terms of cause and effect, you can quite easily link together the ideas of cause and effect that will help us to create an answer for this question. Okay, so basically it's going to be something like this. Once your toy is rotated, the weight is now on the right of the pivot, which causes clockwise moments. And then because there's clockwise moments, this causes the toy to rotate in a clockwise direction back towards its original rest position. Okay, so that is what our final answer is going to look like. Okay, so just like I mentioned earlier on, I hope you can see here how the mind map that we kind of created earlier on about cause and effect helps us to generate this answer here. So just to reiterate, number one is the location of the pivot with respect to the force creates clockwise moments, and then this in turn causes clockwise rotation. Okay, so that more or less wraps up the 3 examples and this introduction to turning effect of forces and moments. I hope that was helpful, and thank you and see you in the next video.